video, we're going to talk about combustion analysis. And combustion analysis is just an analytical technique that we use to determine the composition of a hydrocarbon. So we're basically going to take an unknown composition hydrocarbon sample, we're going to burn it in oxygen, and then use the masses of the products to come back and figure out the formula of that original hydrocarbon. So combustion analysis involves empirical formulas. And we do a quick review of an empirical formula problem before we jump into the combustion analysis. So here we have an example that talks about oxides. We're thinking about bromine, and we have some amount of bromine that's going to react with ozone, which is just oxygen O3, and we're going to get some formula that's a combination of the bromine and oxygen. So we're going to have bromine plus ozone is going to give me some, that's bromine, some bromine oxygen compound. And we know that I'm going to start with this 1.250 grams of this. I don't know how much ozone I'm adding, but I do know that we collect at the end 1.876 grams of the product. I want to know what the formula is of this product here. So anytime we do empirical formula, we need to get mole ratios. So my goal here is to find moles of bromine and moles of oxygen, right? And then once I can ratio those, I can get to that empirical formula. So to find the moles of bromine, the moles of oxygen, we want to go back to just what's happening here. And I'm looking for this product. The product has bromine and oxygen, so if we use law of conservation of mass, I can recognize that all of this bromine is going to show up here in the compound, and then all of this oxygen is going to have to come from the ozone. If this is the mass of my bromine and my oxygen, and I know that this is going to be the mass of all the bromine in the compound, I can figure out my mass of oxygen just by subtracting these two numbers here. So my grams of bromine is this number here. So we're going to use this to find the moles of bromine, and then we're going to subtract these two. So I'll go ahead and do that here. So this 1.876 minus the 1.250. This is going to get me grams of oxygen. So this number is 0.626. And I'm going to use this to get me moles of oxygen. So I have moles of bromine, moles of oxygen, and then we can solve for our empirical formula. So we'll go ahead and do that. So I'm looking for moles of Br. I'm starting with that 1.250 grams. And this is grams of bromine that's diatomic. So I do need to take that into account. So the molar mass here is 159.8. This is for 1 mole of Br2. And for each 1 mole of Br2, we have 2 moles of bromine. I'll just make that look a little better. Okay, so grams of bromine cancel, moles, moles. We end up with our moles of bromine. So this number is 0.015645 moles of bromine. We'll do similar thing for the oxygen. So looking for moles of oxygen, I'm going to start with that mass that we found by subtracting the product from the bromine in the reactants. So we're just going to directly convert that into our moles of oxygen, and we'll end up with this many moles of oxygen. So that's step one when we do the empirical formula, right? We always want to convert whatever form we have in masses to moles. And then our second step, so that's first step. Second step is to ratio them. So we want to ratio the larger number on top, smaller number on bottom. So this is 0.039125 moles of oxygen, and we have 0.015645 moles of bromine on the bottom. Go ahead and plug that into our calculators. This is going to reduce to 2.5 moles of oxygen, 1 mole of bromine. So that needs to be a whole number. So I'm going to multiply top and bottom by 2. We're going to get 5 moles of O and 2 moles of Br. So last step is to actually make or use that ratio to get our empirical formula. So this is going to be Br2O5. So whenever we do that empirical formula, we have that three-step process. First, find the moles of each element in your formula, then ratio based on the smallest amount of moles, and then step 3 is to actually write your formula. So when we do a combustion analysis, we're going to use that same process, but I do want to set up the problem for us. Again, I said at the beginning that we're going to take an unknown hydrocarbon, and a hydrocarbon is just a compound that has carbon and hydrogen in it. So sometimes it has other things. We'll do examples where it also has oxygen, but a basic hydrocarbon just has carbon and hydrogen in it in some ratio. So what we're going to do, we want to figure out what that ratio is, what that empirical formula is. So we do a process called combustion analysis, where we take that hydrocarbon and we react it with oxygen. And when we do that reaction, so this is a combustion reaction. So hopefully you guys remember these from the last exam. So we do a hydrocarbon plus oxygen. If it's combustion, it's going to produce that CO2 in water. And we do this in a nice controlled environment so we don't have extra side products. So we assume that this reaction is happening as written. So in a combustion analysis, you have a furnace. So you'll put your sample in here. Oxygen will flow through the furnace or the reactor here. The reaction will happen, and then your products are going to come out. They're going to leave that chamber here, and the products should be just CO2 and water. So you have something called an H2O absorber and a CO2 absorber, and basically what those two things do is just pull out each of those products. So I can collect all the water here, and I can collect all the CO2 here, and if I can collect it, then I can measure the mass. So the thing we want to recognize for a combustion analysis problem is we're trying to find this. So I want to know that ratio of each of those things. So I want to recognize that all of the carbon shows up in the CO2. All of the hydrogen shows up in the water. So if I can get the mass of the CO2 and the mass of the water, then I can figure out the mass of just the carbon, the amount of just the carbon, and again, using law of conservation of mass, if I know the amount of carbon here, then I also know the amount of carbon here in the reactant. So let's look at a practice problem. So you have mesostyrene, it's a liquid hydrocarbon. So this tells me that this is a combustion analysis problem. The hydrocarbon means that I have just this carbon-hydrogen compound here. So we're going to burn 0.115 grams. So that's this mass. So we're going to start with that much of our compound, and we're going to produce 0.379 grams of the CO2 and 0.1035 grams of the water. We want to know that empirical formula again, so we're looking for this piece here. So as I said, we want to recognize that this 0.379 grams of CO2, all of that carbon comes from the hydrocarbon. All of this hydrogen from the water comes from the hydrogen in that original compound. So our process here, because it's an empirical formula problem, right, our goal, we want to find moles of C and we want to find moles of H. So it's always good to kind of map that out. Empirical formula problem, this is always what our approach is going to be. So to figure these out, I'm going to start with the carbon. So the carbon, I'm looking for moles of carbon. To get that, we're going to use this mass of CO2. So 0.379 grams of CO2. I need to convert that to moles. And then we're looking for moles of carbon, not just CO2. So for every 1 mole of CO2, there's 1 mole of carbon. So I'm going to go ahead and write that step in here as well. And we can set that up and plug that into our calculators. So we're going to end up with 0.0086116 moles of carbon. Then we're going to do a similar thing for hydrogen. So I'm looking for moles of hydrogen, but this time we're going to use the water information, right? The hydrogen shows up in the water. So we have 0.1035 grams of hydrogen. Or sorry, grams of water. We're going to convert that to our moles of hydrogen. So this last step is actually more important than in the previous, right? So for every 1 mole of hydrogen, we have 2 moles of hydrogen. So we need to make sure and double that last piece there. So we plug this into our calculators. We get this many moles of hydrogen. Okay, that's first step in any empirical formula problem. Second step is to do that ratio. So you want to take a bigger amount, divide by the smaller amount. In this case, we just have 2 elements, so this is just one ratio we need. That hydrogen is going to go on top. So we have moles of hydrogen over our moles of oxygen. We want to simplify that. This is going to come down to 1.33. Again, this isn't a clean enough number, so we don't want to leave it. We want to get that to a nice whole number or integer. So we're going to multiply by 3 over 3, and this will get us to 4 moles of hydrogen, 3 moles of oxygen. So last step, final step here is to just actually write the empirical formula from our ratio. And this was not oxygen here, sorry, this is carbon. Fix that. So we're going to end up with C3H4. So combustion analysis problems are basically empirical formula problems where you're getting your mass, not from a mass percent, but from a specific type of reaction problem where you have your combustion analysis. You have your combustion reaction here where your hydrocarbon plus oxygen makes CO2 and water. So it's always going to have that same format. You're always going to be given the mass of the CO2 and the mass of the water. And these are the things that you're going to use to go back and find moles of hydrogen and moles of